So let's look at problem number 9 in page number 11.42 in Aurora. The light is incident on a cathode, and for the two different wavelengths, one wavelength is 4000 Armstrong, other wavelength is 4500 Armstrong, and their stopping potentials are observed to be 1.3 volts and other stopping potential 0.9 volts. They're asking for the work function h mu naught or a phi naught in electron volt of the metal. Okay, so the moment it talks about the full experiment, so E V naught is equal to h mu minus h mu naught. You want the work function phi naught of the metal, so phi naught is equal to h mu minus E V naught. And the potential, let's take the first case, is 1.3 volts. You can substitute V as 1.3 and write E as it is so that your answer is an electron volt. You want to find the electron volt of h mu, h into c by lambda, that's 4000 Armstrong. And you have to have the answer in electron volt, you have to divide it also by E, and therefore you get it like this, and this is your phi naught. But in this sum, I cannot substitute hc by E as 1.2 into 10 to the power minus 6. Why I cannot do that? Because the question says find hc by E. The second part of the question, from the data given below, find the universal constant hc by E. Okay, so that's the issue. And then also work functions. Not only work function, you also have to find hc by E. That makes the sum complicated because we can't substitute this value. So what do we do? This is say lambda 1. For the first wavelength, it's 1.3 electron volt. So let's take the next work function is h into c by E into lambda 2, which is the second voltage. Lambda 2 is 4500 Armstrong of course, and this 0.9. So 0.9 electron volt. Let's solve it like a linear equation. So when you do this becomes a minus. The work function of a metal is not going to change. So it's minus and minus will get cancelled. It will become plus, and therefore 0 is equal to h into c by E into 1 by lambda 1 minus 1 by lambda 2. And this subtraction is 0.9 plus 0.4 is 1.3. So then there's a 0.4, and that's got to be with a negative sign. And so take it, this is equal to this, so hc by E into, let's take LCM, lambda 1, lambda 2 is lambda 1 plus lambda 2 or lambda 2 plus lambda 1. You take LCM, lambda 2 minus lambda 1, okay, is equal to 0.4 electron volt. So then therefore hc by E itself 0.4 electron volt into lambda 1 into lambda 2 by lambda 2 minus lambda 1. So then this is the delta V actually, that's the delta V. So you have a new formula, change in voltage into lambda 1 into lambda 2 by lambda 2 minus lambda 1 will fetch you this hc by E constant. Coming back here, let's solve this at 0.4 electron volt. You have to compulsorily multiply this with 1.6 into, because you need to find the value, right? So obviously, and then it's hc by E 0.4 electron volt into lambda 1 into lambda 2. What is lambda 1? It's 4000. It's 4000 into 10 to the power minus 10 into 4500 into 10 to the power minus 10 by lambda 2 minus lambda 1 is 500 into 10 to the power minus 10. So when you do that, 10 to the power minus 10, 1 of the 10 to the power minus 10 is getting cancelled. So you're left with this is your delta V. This is the new formula that you get, the change in the voltage. Okay, and you know that the hc by E is that you're finding is also in electron volt. So you can leave the answer. You don't have to multiply it with 1.6 and 10 to the power minus 19. Just leave it like that. Because we have assumed everything as electron volt. This also is electron volt. This also is electron volt, and then we are doing the sum. So even though you substitute lambda 1, never multiply it with 1.6. It's a very, very important point. And so then therefore, you get your hc by E on multiplying this. The zeros and zeros here can get cancelled. And 9 5s are 45, and you can this is all solved. Let's look at this. This is a 4 into 10 to the power 3 and this becomes 10 to the power minus 7 into a 4 and a 9, 9 4s are 36 and a 0.4, and you can multiply this and make it 4, multiply and divide by 10, so that you can make this as you can make it as 4. So 4 into 36 into multiply and divide by 10, multiplied, so divided by 10 is 10 to the power minus 8. 6 4s are 24, 4 3s are 12, 13 14 into 10 to the power minus 8, or in other words it's 1.44 into 10 to the power minus 6, the Hc by E's value. Unlike what we memorized it as 1.2 into 10 to the power minus 6, which is a general scenario. But the calculated value based on the wavelength and the voltages plotted turns out to be like this. So using this only, I am supposed to proceed this sum, and I am going to find what is the work function. E V naught is equal to h mu minus work function. The work function therefore is h mu minus E V naught, and to find the work function, h into C by E into lambda minus E V naught. Let's take one of the cases and do the sum. You don't have to take both the cases, and just one of the cases of the voltage where we can take the first case, which is 1.3 and 4000 Armstrong. 1.3 electron volt and 4000 Armstrong, which in the Hc by E you have to write this value, which is 1.44 into 10 to the power minus 6. That's what makes it challenging. By lambda is 4000 into 10 to the power minus 10, and this itself is 10 to the power minus 7, and when this goes up it's 10 to the power 7, and these two together will makes it 10. So it's 14.4 by 4 minus 1.3, and both of them are in electron volt. Okay, so minus 1.3. Let's solve this. 4 3s are 12, 8 3s are 24 minus 1.3. A 3.8 minus 1.3 is a 2.5. So you get the work function to be 2.5 electron volt. This is the answer that I am getting, but the answer has to be 2.3. 4 3s are 12, 8 3s 24, it's 14.4 Hc by E. Yeah, it's 14.4 into 10 to the power minus 6. And we've taken it as 4000 Armstrong, which is correct. Yeah, 4000 for 1.3, just like linear equation, I'm substituting in 1.3. And I get 4 3s are 12, 24, 24 man, 6 4s are 24. So then we sorted 3.6, 1.3 is 2.3, so the answer is 2.3 electron volt. Beautiful sum. You cannot proceed using the previous method because the question is to determine Hc by E and therefore finding the work function. That makes the sum a little complicated. So then let's go to next question. So the next question that I would like to do is 8th question, very very important CBSE question. When the light of wavelength 400 nanometer is incident on a cathode of the photocell, the stopping potential is given to be 6 volts. The wavelength of the incident light is going to be now changed to 600 nanometer. Find the new stopping potential. What will be the V naught for this one? This is, let's keep it as 1 for the wavelength 1. Let's keep this as stopping potential 2 for this wavelength. They ask you for this. Let's do it like a normal linear equation. E V naught is equal to h mu minus h mu naught. That's considered for first one. The frequency is 1. For the first wave, it's h into c by lambda 1. And you want the answer in electron volt. Then ideally you should write it as okay, what are they asking? Calculate the wavelength of the, calculate the stopping potential, right? So you want, you could have brought this E down. So since they're asking for stopping potential, V naught 1 is equal to h mu 1, which is c by lambda 1. And the E can be brought down, minus this itself is work function, h mu naught itself is work function by E. Because in this I can substitute this as 6 volts because it's been given. is equal to hc by E. You know the value of hc by E. In this sum I can substitute because they didn't ask me to find that. So it's 1.2 into 10 to the power minus 6 by lambda 1 is 400 into 10 to the power minus 9 minus work function we don't know, but still there is an E. Leave it like that and form this as a first equation. Let's do the next equation where there's an unknown voltage for the next wavelength, this wavelength. So it's 1.2 into 10 to the power minus 6 by 600 into 10 to the power minus 9. Substituting that this is lambda 2, considering this is lambda 2. So then therefore, let's write the formula therefore. And let's write this let's using the second potential VO2, H into C by E, lambda 2 minus phi naught by E. Using that, let's write this unknown voltage is 1.2 into 10 to the power minus 6 because it's C by E by lambda 2 600 into 10 to the power minus 9 minus phi naught by E. Don't panic that you don't know phi naught by E. It's going to get eliminated because we're going to subtract this and subtract this, or in other words put a negative sign, this get cancelled. So you get 6 minus V is 1.2 into 10 to the power minus 6 by 1 by 400 into 10 to the power minus 9 minus 1 by 600 into 10 to the power minus 9. So we have something like this. You can, what you can do 6 minus V, and you can take the 10 to the power minus 9 out in both the cases is common. So 1.2 into 10 to the power minus 9 goes up, it will become 10 to the power 3. And you also have a 1 by 400. Let's take the 10 to the power 2 out from the 400 and 600. So 1 by 4, 1 by 6. So this and this get cancelled. So you get 6 minus V is equal to 12 into 1 by 4. This LCM is 12 and 4 3s are 12 and 6 2s are 12. 12 and 12 get cancelled. 6 minus V is equal to 1. So V is equal to 5 volts. So the unknown voltage for that particular second wavelength becomes 5 volts. Okay, such a beautiful sum. Solve it like a linear equation. So next question is the problem number 7, where the X-rays fall on a photosensitive surface, cause photoelectric emission, assuming that the work function of the surface is negligible. Oh, so the work function H mu naught is 0, and work function negligible. X-ray is falling. Okay, assuming work function of the surface is neglected, find the relation between the de Broglie wavelength lambda of the electron emitted. It is called it as lambda E instead of the emitted to the energy of the incident photon. You're going to associate lambda with the energy of the incident photon. You need to find a relation. Initially, we found a relation between lambda E and lambda. There was some relationship where there was lambda E square, and we found lambda and stuff like that. We have done previously 2 sums based on that. Okay, wherein we found that lambda is some constant into lambda E square, where this turns to 2 mc by h. 2 mc by h is this constant, if you remember. Okay, so we have done that proof, but here it's energy relation. So when they're talking about incident photons energy, you know that incident photons energy, when this is negligible, obviously the entire photon's energy will go about in increasing the kinetic energy of the electron. So you know that you have to write that statement, the entire incident photon's energy is what is going to be equal to the kinetic energy maximum, or a half mv max square. Correct? Okay, so then this is the kinetic energy of the photon, which gets passed on into the kinetic energy of the electron. And the kinetic energy of the electron, you know that P is equal to root of 2m kinetic energy. So squaring both sides, you get 2mk, and this kinetic energy maximum, this is the kinetic energy, which can also be written as P square by 2m. And not sure of the sum. Okay, let me think about it and tell you. Okay, sorry, let me continue. You know that the incident energy gets completely transferred into kinetic energy. Okay, and you know that the momentum of the ejected particle is a subatomic particle, which is equal to root of 2m kinetic energy. But this is the kinetic energy of the electron. But the kinetic energy of the electron is nothing but the kinetic energy of the photon. So I can always write, they have given 2m kinetic energy of the photon. They are calling kinetic energy of the photon as E mu, something like this. So then substitute this kinetic energy of the photon. The energy of the photon is E mu is what they are saying. So substitute it here. So once you do that, you substitute lambda is equal to h by p is the de Broglie wavelength of this electron, lambda e or lambda, which is h by root of 2 m e nu. So can you see that the wavelength of the electron and the incident energy are inversely proportional, and also square root of incident photon. This is the relationship. Please understand this relationship. This is valid only when the work function is 0. Not otherwise. They could ask you these things in assertion reasoning. So if they ask you to plot a graph between the wavelength of the electron and the kinetic energy, the energy of the incident photon, it is inversely proportional. You can call it lambda or lambda e in the sum. The lambda e is referred to in the sum as lambda. Okay. So that's about that sum. So let's go to next problem, number 6. Obtain a relationship between stopping potential and frequency. That's okay. That's the relationship I already taught you. X-rays of wavelength 0.82 Armstrong falls on a metal surface. Calculate the de Broglie wavelength of the emitted electron. De Broglie wavelength of the emitted electron. Neglect the work function of the surface. Oh, you know, the moment you neglect the work function of the surface, there is a direct relationship between the wavelength of the electron and the wavelength of the incident light. We just saw that the lambda, which is the wavelength of the incident light, is proportional to lambda square, and there is a constant that it is 2mc by h. Where did I write that? Okay, I'll just see that there is a relationship that we have already proved, in which we have always been considering that 2mc by h, oh my god, yeah, 2mc by h into lambda square, and this is the proof that we have always done. And if you could memorize this, the advantages, this is the lambda of the electron and this is the lambda of the incident wavelength, and this is related like this, then it becomes very easy for you. The question is about lambda of the electron. So what is lambda of the electron from this? I'm not even using my brain, I'm just using this and trying to do it. If I get the answer, it's good. So lambda e square is lambda into h by 2mc. Okay, and lambda is the incident wavelength Armstrong, which is 0.2882 into 10 to the power minus 10. Planck's constant, you don't know h by c, right? 6.6 into 10 to the power minus 34 by 2 into m is the mass, and c is, what do I substitute for this? This question, it was completely talking about photoelectrons only, no? So this is completely about photoelectrons, and so can I write the mass to be, I'm just trying, okay, 9.1 into 10 to the power minus 31 into speed of light is 3 into 10 to the power 8. Would this help me? And then finding a square root, will I get lambda e? Just a thought, okay? Not necessary that you're going to proceed like this. Okay, so this will be, this and this get cancelled, becomes 3.3, and this and this get cancelled, you get 0.41. So thus you are left with a 0.41 into 3.3 by a 9.1. Let's consolidate all the 10 to the power. This becomes 10 to the power minus 44, and this becomes 10 to the power, there is an 31 minus 8 is 11, and this is 3, and there's a 10 to the power minus 23 at the bottom. And when it comes 10 to the power 23, so it will become 10 to the power 21, isn't it? It's 10 to the power 21. Okay, so to make it as an even power, what I can do is just let's multiply, make it 41 by multiplying by 100, 10 to the power 2, make it 33 by multiplying by, so totally in my 10, so 10 to the power 3. So 10 to the power 3, 10 to the power 21 minus 10 to the power 3 is 10 to the power 18, that made it even. By 9.1 we have, let's multiply 41 and a 33. 41 and a 33. Can I assume this is 9.0? 9 9s are 81. No, 9.0. So can I cancel this by 3 and cancel this as 11? And so then this becomes root of 11 ones are 11. 11 fours are 44. 45 by 3 into 10 to the power 18. I go wrong. I want to try this. Okay, 3 ones are 3. 15 5 threes are 15. And a 0. And again 3. And just forget it. I can approximate to 150. Into 150, and this can come out as 10 to the power 9. A square root of 150. A square root of 150. You can pair it up like this. 1 ones are 1. Then bring the 50 down and add the 1 and 1, which makes it 2. You decide on this number which has to come. It can be 22 2s are 44. So it will become a 6. Beyond which you have to keep a decimal and add 2 zeros and add 22 with a 2, which makes it 24. And so can I approximate it to 12? 12s are 144, right? So can I approximate it to 12.2 into 10 to the power 9? And that's what I'm getting it as a lambda of an electron. But let me see what is the answer here. So then they are writing this in Armstrong, which is 10 to the power. 10 to the power, what happened? It's not, it's positive, is it? Minus 31. This is 10 to the power minus 10. This will be minus 44. Minus 44. And this 31 minus 8 is 23. So it should be negative, right? Shit, I made a mistake. Calculation mistake, I'm sorry. So otherwise I think I'll get my answer right, but provided you know this formula, it becomes very easy. And this formula can be applied only for the work function is negligible. So then you're trying to find a lambda square is lambda into h by 2 mc. So this lambda e is root of this, and lambda is given to be incident radiation 0.82 into 10 to the power minus 10 into h 6.6 into 10 to the power minus 34 by 2 into 9.1 into 10 to the power minus 31 into 3 into 10 to the power 8. Let's do the calculation again. This powers is 44 minus 44, and these 31 and 8 makes it, this is 3 and this is 23 and this is a minus 23, and when it goes up it becomes plus 23, and so then it becomes 1 to 21. So it's 10 to the power minus 21, isn't it? And you have a 0.82. You know, you can cancel this as 3.3. You can cancel this as 0.41, and you can approximate this to 9. The best part of approximating this to 9, you can just take it out as 1 by 3 square root. Okay, and within the root you are having 0.41 into 3.3. Okay, you have 3 is getting. No, again, this is 3 into 10 to the power 8. So when this cancels, it will become 2.2. So it's actually, so what am I ending with? I'm ending with a 0.41 into 2.2 is all I have, because I've taken this 9 out as 1 by 3. Yeah, it's sorted. Okay, so then therefore what is this into 10 to the power 21? You want to make it as even power. It's multiply this with 100. This with the 10, so 10 to the power 3 you multiply, so you also have to divide it by 10 to the power 3, which makes it 10 to the power minus 24. So this will become 10 to the power minus 12 outside, and so you also have 1 by 3, and this is 41 into 22. 22 ones are 22, 22 fours are 88, 88, so it's 90. So can I say it's root of 902, and can I approximate it as 900, so that I can approximate it as root of 900, and 30 into 30, so 30 by 3. So can I write 10 into 10 to the power minus 12? So this is if I want to write this answer in Armstrong, which is 10 to the power minus 10, is 10 into 10 to the power minus 10 into 10 to the power minus 2, which makes it 0.10 into 10 to the power minus 10, or a 0.10 Armstrong. This is the value that I'm getting here, and let me check with the book back answer. I've slightly approximated though. Okay, so then let me check what is the answer that he has given. 0.0995. They are saying 0. Okay, answer is correct. 0.0995 Armstrong, which is closer to this. So I use this formula. It was very easy for me because I already have learned this relationship. It became very easy for me. Okay, so remember that this condition, that 2mc by h into 2mc by h into lambda e square is lambda. If you can remember that, well and good. Okay, so you don't have to really use any other method which is given in Aurora if you're clear with that concept. Okay, so let's go to next. The next sum that I would like to do is this sum which has been repeatedly coming for every exam. Calculate for problem number 43 in page number 11.39, where calculate the ratio of accelerating potential required to accelerate a proton and alpha particle to have the same de Broglie wavelength. So the de Broglie wavelength of the proton should be equal to de Broglie wavelength of the alpha particle. The formula for de Broglie wavelength is h by root of 2m mass of the proton, 2m. If they're talking about potential, calculate the ratio of accelerating potential. So I have to write not kinetic energy, I should write EV naught, the accelerating potential. This is for the proton, which is also equal to h by root of 2 into mass of the alpha particle into charge of the alpha particle. It's actually the charge of the alpha particle into the stopping potential. And this stopping potential, the ratio is what they're asking. So this is for a proton. Let's consider this as V1 and let's consider this as V2, which is for a proton, and we can write this as an V alpha. So that we can now you know that we can find the ratio of the accelerating potential. So we can divide lambda. Both are equal. No? They both the de Broglie wavelengths are equal has been given. So cancel this. Therefore, you get root of 2 into mass of the proton into charge of the proton. You know, charge of the proton is just E. The voltage of the voltage accelerating the proton is also given. 2 into mass of the alpha particle is 4 times the mass of the proton, and the charge of the alpha particle is 2 times the charge of the proton. Okay, and then there is a V alpha. So squaring both sides, you know, the 2 and 2 get straight away cancelled. The E and E also get straight away cancelled. The MP and MP also get straight away cancelled. You get VP is equal to 4 to the 8 V alpha. So it's VP by V alpha is 8:1. The stopping potential of VP by V alpha is 8:1. This is the way I would do this sum. Don't look at the way Aurora has done. It's unnecessary points have been given. So that is example 43. Let's go to example 40. The problem number 42. An electron and a proton. So here in this sum, it's an electron and a proton having a de Broglie wavelength of 1 nanometer. So you know the de Broglie wavelength of an electron is 1 nanometer. This is also having, so they both are having an equal de Broglie wavelength only. Write the ratio of linear momenta. Linear momenta means mass into velocity of the electron, and the mass into the ratios of this is what they are asking. So you know the de Broglie wavelength of an electron is h by ME into VE, and de Broglie wavelength of a proton is h by M proton into V proton. They are asking for the ratios of momenta, which is basically this and this. Okay, which is lambda E into h by. Okay, so the ratios of the momenta. This is the momenta PE, and this will be the momenta of the proton, which is PP. So then I don't see anything because both of them are having the same wavelength. So which means is 1:1 is all I can say. So all I can say is therefore the moment of the electron and the moment of the proton is in the ratio 1:1. So there is also another question. Compare the energy of the photon with the kinetic energy of the electron. Compare the energy of the photon. Energy of the photon is E mu. H mu, which is E. Energy of the photon is E mu, which is H mu. Energy of the photon with the kinetic energy of the electron. The kinetic energy of the electron is kinetic energy is half mv1 square. Okay, we also know, but I can't say that this is equal to this unless they give the work function is equal to 0. They didn't specify anything like this in the sum. An electron and a proton have a de Broglie wavelength of 1 nanometer. The ratio of the linear momenta. Compare the energy of the electron and a photon. I'm sorry. This is not a proton, it's a photon. So incidentally, I got the same answer, no problem. It's not a proton. So because I was thinking the mass of the electron and the mass of the proton will be different, but it's not proton. Mass of the proton is it's photon. Okay. So then therefore it's fine. It's not a proton, it's photon. Please correct it. And so then now you have to compare the energy of the photon with the kinetic energy of the electron. Energy of the photon is h mu, which is h into c by lambda. Energy of the photon, energy of the photon is equal to Pc. Energy is Pc, sir. You remember this? So when you talk about photons energy, it's electromagnetic radiations. So the formula for energy is equal to Pc. So you have to compare this and this, is it? No, this is hc by lambda. Then kinetic energy of the electron. Okay, it's about kinetic energy of the electron. Kinetic energy of the electron. Let's write it using this formula. Momentum is equal to root of 2m kinetic energy. So p square by 2m is the kinetic energy of the electron. So because this question is talking about momenta, therefore I have to choose this formula which relates to kinetic energy. So the kinetic energy of the electron is p square by 2m, and the ratio of it is what they are asking. So the ratio of the incident energy, the energy of the photon by the kinetic energy of the electron is h into c by lambda by can I say p square by 2m. So then can I multiply this up? Can I say it's 2mhc by lambda into p square? Okay, can I say this? And what else I can do? Can I write this p square as mass into velocity? And so therefore can I write lambda into, I'm just thinking, can I write this p square as lambda c by kinetic energy is p square by 2m, it's c by lambda by p square by 2m. So when I find the ratio, it's 2m lambda 2m hc. No. Instead of this is what I got. One second. See, they seem to be writing what is p square from this. Lambda is equal to h by p. So p is equal to h by lambda. P square is equal to h square by lambda square. On substituting that, you get 2m hc by lambda into h square by lambda square, where this lambda get cancelled and this lambda goes up. One of the h get cancelled. So you get 2mc lambda by h. 2mc lambda by h. According to me, it's a very difficult sum. A comparison of the incident energy with the kinetic energy. This is incident energy of the photon versus the kinetic energy of the electron. And you see the 2mc h and all is a constant. So there's only this wavelength lambda, which is the incident wavelength energy. The ratio depends only on that. something that can be observed and understood. It's very difficult. It's not as easy as it seems. If this question comes, I would definitely struggle I would have struggled in the exam. I'll teach you the sum once again, 40-second sum. An electron and a photon's ratio momenta is 1:1. Since the question talks about momenta, they're asking you to compare the energy of the photon, which is E mu, which is H mu, which is H into C by lambda, with the kinetic energy of the ejected electron. And the kinetic energy of the ejected electron in terms of momentum, since the question talks about momentum, is 2m kinetic energy. Therefore, it is p square by 2m is the kinetic energy. And a comparison of this with this is the question. So I thought, okay, let me just do E mu by kinetic energy of the electron, which is directly be hc by lambda by p square by 2m. I thought the sum is going to be that easy. So I get 2m hc by lambda into p square, and this is where I got into a stumbling block, where I should write what is p square. By de Broglie wavelength, lambda is equal to h by p is equal to h by lambda, and so then therefore this can be 2m hc by lambda into h square by lambda square, where lambda get cancelled, this lambda goes up, h and h get cancelled. So you get 2m lambda c by h is the ratio of the incident photon with the kinetic energy, and it's quite difficult for me. I hope you understood. As long as it's a proof, we'll be able to definitely write this answer. If they say prove that, then we can manage. And okay. Oh, it's not over. You need to substitute the value. Oh my god. By h. Okay, you need to substitute the respective values and write it also. Okay, so this has come in a CBSE paper. The second part of the question I would have struggled. 1:1 was pretty easy. Okay, so then that's about it. Let's go to the problem number 41. Problem number 41. Why is the frequency and not the intensity that determine the photoelectrons effect will occur? Because frequency is only related to energy. Intensity just means number of photons. Number of photons has got nothing to do with the energy. So it's a frequency which is the determining factor in the photoelectric current. That's all. And so let's go to problem number 40. What reasoning led de Broglie to put forward the concept of matter waves? De Broglie put forward the bold hypothesis that the moving particle of matter. So moving particle of matter, every matter behaves like, that's what I told you, as a particle and wave. Make sure you're saying that a moving particle of matter behaves like a wave and like a particle. Okay, should display dual nature. This should display wave-like properties. A moving particle of matter exhibits wave nature also. So that's what it is. Under suitable condition, he reasoned that nature was symmetrical and that the two basic physical entities, matter and energy, must have similar characteristics. This is a very important point. He reasoned that the nature was symmetrical. Yeah, we know that nature is very symmetrical, and that two basic physical entities such as matter and energy must have symmetrical characteristics. So these two must have symmetrical characteristics. And if the radiation show a dual nature, if the radiations is going to show a dual nature, so should the matter also. If this is dual, this is also dual. No? The symmetry has to exist between matter and energy. And so if this is behaving like a wave, the matter should also behave like a wave. If this is behaving like a particle, the energy should also behave like a particle. So then there is a dual existence, and that's what he's trying to say. So you have to write this as a reason. You should say that there is a whole lot of symmetry in the world. Nature is so symmetrical, and therefore the two basic physical entities such as matter and energy should also have a symmetrical characteristics. If energy can be wave nature, matter also can be wave nature. That's all. So that's what gave rise to the phenomenon of De Broglie's hypothesis. So second question, there's a B, this is the A part of the question, and there's a B part of the question where the wavelength lambda of the photon and the de Broglie wavelength of an electron of mass have the same value. The wavelength lambda of the photon, please, not proton, I'm sorry, I'm making the mistake answer one second. Photon, which is the incident radiation, and the de Broglie wavelength of the electron, we know the relationship. Okay, we already know the relationship, lambda E square, and 2 mc by h is what is lambda of the incident photon, and this is the relationship already know. Okay, so then the wavelength lambda of the photon and the de Broglie wavelength of an electron of mass m have the same value. The wavelength of the electron of mass m have the same value. We learned that they're not having the same value, but that was based on the work function being 0. I think we found this only by using the phenomenon where the work function was 0. Okay. So I have my own doubts about doing this sum also in the way I taught you. Where is this? Using this formula. Unless I can't use this formula unless the work function is 0. Did they specify anything like this in this question is something that I need to look for. Sixth question. Where is that sum? Sixth question. X-ray of 0.82 falls on a metallic surface. Calculate the de Broglie wavelength of the emitted photon, neglecting the work function. So I could use that. But in the sum, they have not specified anything like neglecting the work function. So then this question, the wavelength lambda of the photon and the de Broglie wavelength of an electron of mass m have the same value. Show that the energy of the photon is 2 lambda mc by h times the kinetic energy of the electron, where C and H have the usual meaning. Okay, they're comparing the kinetic energy of the electron with the incident incident energy of the photon. They wanted this relationship. Okay, so what do we do for this? But there is work function. There's no work function. None of this matter has been given in this question. So then therefore I can't use that formula. I have to think about the sum. And as usual, you know that the incident photon wavelength of the photon is given and the energy E mu can be written as h into c by lambda of the photon. Or in other words, just lambda itself means it's only the photon's wavelength. Okay, and you know that they have also given the lambda of the electron, which is the de Broglie wavelength, which is h by mass of the electron into velocity of the electron, or h by p. In other words, it's h by p. And that P can also be written as, you need the kinetic energy of the electron because you're comparing energy versus kinetic energy, the incident dual photons energy versus kinetic energy. So write it as 2m kinetic energy. So then what is kinetic energy from this equation? Lambda E is equal to h by 2m kinetic energy. Or let's not talk about lambda. We'll simply, because they said lambda of an electron, therefore I'm forced to write lambda of an electron, which is de Broglie h by root of 2m kinetic energy. Let's find what is kinetic energy from this. Let's square this. H square by 2m kinetic energy. Therefore kinetic energy is h square by 2m lambda E square. And I need to find the ratio of this and this. Let me try. Energy of the photon by the kinetic energy is h into c by lambda by h square by 2m into lambda E square, where the h and h get cancelled and this goes up, and lambda E cannot be cancelled, you know that. So it's c into 2 into m into lambda E square by lambda into h. Lambda E is the wavelength of the electron. So you still get 2mc by h, but in addition there is a lambda in this. Okay, so let's see if that's what they're asking. 2mc. Show that the energy of the photon is this much times the kinetic energy. They seem to have cancelled the lambda. How can you cancel the lambda? How can you cancel the lambda? Because in this question they gave that the lambda is equal. The wavelength lambda of the photon, the de Broglie wavelength of electron or mass m have the same value. Since here they are saying the lambda of the electron, so you can cancel this and this. You can write lambda E to be lambda only. So 2mc into lambda by h is a proof, and thus the frequency energy of the incident radiation by the kinetic energy is this much times, okay, or energy of the photon is this much times the kinetic energy. Very, very good question. But here I am not, the main point is they didn't specify anything about the work function. When they don't specify anything about the work function, then I should avoid using anything to do with the work function. I should just use the de Broglie wavelength formula of the electron. Okay, so then that's the moral of the story. So then I'll go to the next question is problem number 39, where a proton, this is really a proton and an alpha particle. An alpha particle is helium, okay, and have the same de Broglie wavelength. Lambda of the proton is equal to lambda of the alpha particle. Determine the acceleration potential. We just did it. It's h by acceleration potential root of 2 into mass of the proton into potential charge of the proton into voltage of the proton is equal to h by root of 2 into mass of the alpha particle is 4 times the mass of the proton. Charge of the alpha particle is 2 times the mass of charge of the proton, and so the voltage of the alpha particle, h and h get cancelled, the 2 and 2 also get cancelled, and the mass of the proton, and charge of the proton. Okay, so then thus you have Vp is equal to 8 into V alpha. Vp by V alpha is 8:1. I think we did this sum before. 4 2s are 8. This is proton and this is proton and an alpha particle. Proton and an alpha particle. Yeah. So we found the ratios of the velocities. That was the first question. Then there is also another question. The ratios of their potentials is what we found. Okay, because this stands for potential. And then they're also asking for ratio of the velocity. So they're asking for the ratio of the velocity. The de Broglie wavelength is the same. So it's lambda is equal to h by mass of the proton, velocity of the proton is equal to h by mass of the alpha particle, velocity of the alpha particle. All I know, h and h get cancelled. So mass of the proton, velocity of the proton is 4 times the mass of the proton. Mass of the alpha particle is 4 times the mass of the proton into V alpha. MP get cancelled. Velocity of the proton by velocity of the alpha particle is 4:1. So that's another question. So there's one more question, which is problem number 38. Plot a graph between lambda and 1 by root V. You know, lambda is equal to h by root of 2m EV, which shows that it's inversely proportional to root V. But if they ask you lambda versus root V, you can do this. But this is 1 by root V, therefore it is linearly proportional. But the question doesn't stop here. Okay, which is accelerated through potential for two particles A and B carrying masses m1 greater than m2. So there's m1 and m1 is greater than m2. Which one of these represents a particle? They've given the graph itself. See, let's see, this graph has been given. They're saying that this is m2 and they're saying that this is m1. And they're saying m1 is greater than m2. And this is a greater mass. And Which one of these two represents a particle of smaller mass? Oh, the question is okay. Carrying charge but of mass m1 and m2, where m1 is greater than m2. Which one of these represents a particle of smaller mass and why? What is smaller mass? Then why did they given the question m1 is greater than m2? We are supposed to determine which mass is bigger, correct? You don't understand. Okay, so you know that lambda is equal to h by root of 2 mev, correct? And so can you see if the mass is going to change? If mass is going to change, and lambda is inversely proportional to mass, correct? And okay, if what can I say? So to determine which one has got greater mass, let's write it like this: h by root of 2 m e 1 by root v. Let's separate this out because this graph is between this and this, and so lambda versus 1 by root v is a straight line graph. So you will obviously get a slope in this, which is opposite by adjacent or whatever. So then can you see a lambda by 1 by root v will turn out to be the slope, and the slope itself is h by root of 2me, and this is the slope. Okay, if this is going to be the slope, or a lambda into root v itself is this graph slope, which is also h by root of 2me, and the slope is inversely proportional to mass, inversely proportional root of mass. And so whichever has got a greater slope will have a lesser mass. Which has got a greater slope is m2 has got a greater slope, and so it will have a lesser mass. So m2 should be lesser than m1. So this is how you have to identify. It's an excellent sum, excellent sum. Please go through this once again. You write this de Broglie wavelength relationship. Okay, and take the 1 by root v out. So this is y-axis and this is the x-axis, and y is equal to mx. And so the m itself is so much, and the slope is inversely proportional to mass, and therefore you also should know that this is also the slope of 1 by root v graph. You just get to know it, okay? It's a very, very important question. So there are many, many sums like this, okay, where you can try all these sums. And arrive at your answer. You can try the 37th, 36th, 35th. Don't leave any stone unturned, okay? 33. It's all repetition, so I'm not doing. So otherwise, there are so many graphs which has been given to identify which graph is correct and where which is got higher frequency and sums like that. Okay. So you have to look at those sums also. Probably we can discuss in the class later. But I'm unable to do it now. It's too much to do. Okay, so I'm winding up the recording.